Hi, I'm Torsten, and I'm presenting joint work with Zuzana Kukelova. We're interested in the visual localization problem. We want to estimate the position and orientation from which a query image was taken in a known scene. Visual localization methods should be compact, resulting in representations that occupy as little memory as possible. The estimated camera poses should be accurate, within a few centimeters and below 1 degree in error, and the localization process should be efficient. In this work, we mainly focus on compactness and accuracy, mostly ignoring efficiency. When it comes to accuracy, state-of-the-art methods are structure-based. Given a 3D model of a scene and a query image, they establish 2D 3D correspondences between pixels in the query image and 3D points in the scene. These matches are then used for camera pose estimation by applying a camera pose solver inside RANSAC. Here we consider explicit scene representations based on structure for motion point clouds. In order to achieve compactness, we use structure compression. We are selecting a subset of the points such that pose accuracy remains as high as possible. Ideally, we would like to select a minimal subset of the original 3 points, such that we can still estimate accurate camera poses for the query images. However, this is a very hard problem to solve, especially since we don't know the query images by the time we compress the structure. Prior work thus aims at selecting small or minimal subset of points under certain conditions. This typically involves solving a potentially complex optimization problem, but ignores camera pose estimation accuracy. In contrast, we aim at selecting a subset of points that is likely to lead to good pose estimates without making any guarantees on minimality. The input to our approach is a structure for motion model, which defines which database images observe which 3 points, and we want to select a subset of 3 points such that each database image sees at least n points. Our main idea is to not select points individually, but rather consider a triplet of points. For a given database image and a given triplet, we can estimate the camera pose of the database image and compare it against the ground truth pose. We can then decide whether a triplet leads to an accurate pose or an inaccurate pose estimate. Similar to prior work, we thus make the assumption that the distribution of query poses is similar to the distribution of database poses, which seems to be a valid assumption in many cases. Our main contribution is an approach that we call trivial triplet sampling. For each database image, we randomly sample 10,000 point triplets of the points visible in the database image. For each triplet, we estimate the camera pose of the database image using 2D 3D correspondences readily provided by the structure for motion model. We sort the triplets based on position errors, filter them to get rid of triplets with large pose errors, and finally go through the sorted list and select triplets until at least n unique 3 points have been selected for that image. This is trivial to implement, and we actually propose multiple variants in the paper that we are not going to discuss here. We compare our compression scheme, which are the blue and red curves, against prior work on structure compression on multiple datasets. Here the x-axis shows memory consumption and the y-axis is pose accuracy, the percentage of images localized within a given error threshold. Better results at the top and to the left. Each method has a single parameter to control memory consumption, and we obtain curves by varying this parameter. As you can see, our methods offer a better pose memory consumption trade-off than prior work, and this also holds for other scenes. We also integrated our compression approaches into both a hierarchical localization pipeline and a pipeline that directly matches 2D features and 3D points without image retrieval. We compare against full pipelines for compact localization, which combine structure-based compression with descriptor compression. These methods contribute on the descriptor compression level, and to compete, we use standard product quantization for our approaches. As you can see, our simple structure compression methods leads to state-of-the-art results. In particular, we obtain competitive pose accuracy using as little as 0.5 megabyte on Aachen. Note that our approach can easily be integrated into the other methods to replace standard structure compression schemes used by these works. If you're interested in trying out our method, code is available.